Forward to talking to all of you. And yeah, also, there were various technical questions and everything. So very happy to answer, very happy to discuss any ideas you have that you want to brainstorm. Yeah, so looking forward. Yeah.
Okay, so I'm just setting up the agenda for today call. So in first session, we will be so we have designed two examples notebook where we are using the API, and we will walk through that notebook how we are getting the data and plotting it. So in first example, we are fetching the data based on we are fetching the tehsil data based on the lat long and plotting the cropping intensity by accessing its layer. And then in second example, we are plotting water balance by using by fetching the data by using lat and long. So, and in second session, we are taking, so Dr. Said will be taking the various questions, and many of you asked the questions around the how we are getting this data and what is the more technical details of these data source and the algorithm. So he can answer all of these questions. So, okay, we can begin. So I'm sharing my screen first. Mm. Eddie sir, can you give me the right sharing right?
Yeah, try now.
Okay, perfect. Okay, so the first example I'm taking is we are fetching the
Sorry, Kapil, we should record also. I forgot to. Oh, it's already recording. Okay,
already
okay.
recording.
Cool. Take it. Yeah.
तो वो start हो जाता है automatic. So in first example, we are plotting the cropping intensity and getting this data by lat long. So this is notebook and it is available. We'll share the link also after this call, and you can access it. Is publicly available. So in first cell, we are obviously importing some necessary libraries to plot it, and I'm going to the code part. So in second cell, we supply this latitude and longitude and define this base URL for our API endpoint and define these parameter lat long MWS API point. So basically, we are setting up the endpoint here and MWS data API endpoint. And this is the API required API key. So we'll remove this API key after the call. You can just copy this and use it as it is by using your APIs. And we already showed you during our last session how to generate the APIs key. And I'm just running this cell. Now we are setting up headers. So to use this API key, we need to send this header with the API X API key and then the API key. So first we are getting the state district tehsil name by using latitude and longitude. So we'll pass the latitude and longitude and API will return the state district and tehsil. So in this, I'm just building the URL by joining base URL plus lat long MWS API point, and I'm hitting this by using the request library. So if I got the response correctly, then I'm storing this response in this variable response data MWS lat long. So I'm just running it. Okay, so as you can see, messages API call successful, and we received the data. Okay, so in next API, in next cell, I wrote a function in which if you supply this response, it will form the request parameter for next API. So from rest, I'm defining a dictionary, and from this, whatever response we got, I am fetching state, district, tehsil, and setting this up. So if I will run this, it's defined. I'm hitting this. So in first, I am passing this response data, and I am setting up the setting up the endpoint for the next API to get the data. So basically, it is base URL and MWS data API endpoint, which is get the seal data and hitting this API. So let me just run it. So this response we received. So lat long it resolved to Rajasthan district, Bhilwara, Mandalgarh, and UUID. So it also returned this UUID is MWS ID. So it returned MWS ID of that lat long also. The state district block and MWS ID of that lat long micro-watershed ID, which we already explained you during our last session that it is unique. So this response I generated to hit the next API get MWS data where I passing this MWS UID and state district tehsil and it returns all the data related to that MWS aquifer and it have many all of our variable precipitation, hydrological variable, drought variable. So from that we picked cropping intensity. So if you see, we just getting the response date from response, we are getting this cropping intensity annual. And in final plot, I defined this a function in which if you supply the data, it will give you the plot. So basically, this is our final cropping intensity plot, which is showing how much percentage area in single crop, double crop for that particular micro watershed. So this plot is basically showing you the cropping intensity over the years 17, 18, 18, 19, 19, 20. So this, okay, if you have any doubt, you can ask.
Uh, Hi Kapil, I'm Sandeep
Yes, Sandeep.
speaking. So, how are you managing the things during Kharif season, like when we have a cloudy conditions?
Uh,
Uh,
Sandeep, actually, it will be great. Where are you from, Sandeep? If you can also just introduce yourself. I wasn't here earlier.
Yes, sir, sir, I'm Sandeep from Aquacarta. I came to your meet with the Sudesh Menon and Manish ji. Right.
Oh, okay, okay. Yeah,
Yeah.
great, Sandeep. Yeah.
Yes.
Yeah, so actually, we are taking data from multiple satellites, right? So there's Sentinel-2, which provides optical data, and
Mhm.
also Landsat. And with Landsat also there are multiple, right? There's Landsat 9, there's
Yeah.
8, yeah, 7 is now defunct. So the time we basically compose time series on a fortnightly basis. Yeah.
Okay, sir. Right.
And we chose this unit of fortnight because it's quite probable that some or the other satellite might be available, right? So
Mm-hmm.
if, when Sentinel did a passover, if it was cloudy, maybe Landsat, one of the Landsat may have picked it up. So Sentinel has a return period of about 5, 6 days, and Landsat has a return period of about 16 days. Yeah.
Yes. Mm.
So there is a chance that at least one of them might have given a data point in that fortnight. Yeah.
Okay, sir.
Then there is a harmonization that also happens
Mhm.
because although all of them are measuring the same bands, they measure your near infrared, red, green, blue, and those are together used to derive NDVI. But there can be
Mhm.
minor sensor calibration issues between all of them. So this is where a lot of people have done that kind of research of how to calibrate sensors of different satellites with each other. Yeah.
Yeah. Mm.
So that part we've implemented that we basically harmonize everything to Landsat at that
Mm.
scale. Yeah. So that helps. And then further, if there is still any missing data, then we interpolate. Yeah. So if from one fortnight to the other, there is some fortnight in between gets missed, then we fill it through interpolation. Yeah.
Right.
And what we saw in this particular graph is basically the total. Yeah, the
Yeah.
total ET and so on. So that is basically just a sum of the values over all the fortnights in the year. Yeah.
Yes, sir.
हिस्ट्री चले जाएंगे ना, मेरे हिस्ट्री
Okay.
चले जाएंगे, भेजो तेरे अकाउंट का, तो तेरे अकाउंट में रहेगा ना।
Kapil, maybe one of you can mute, I think. Yes. Yeah.
Yes, sir, you're absolutely right. So can we utilize Moody's data like that is daily available? Okay, and that has a
Yeah.
resolution of 250 meters as well. So,
Right, right.
yeah.
Hmm.
So from a MSW point of view, we can also generate the intensity using Moody's and DVI.
Yeah, correct. So we also do use Modis for gap filling. But one of the problems that Modis can have is that because the resolution is at 250 meters, so it may not be very accurate at a farm level.
Right,
Yeah,
right.
but exactly at a micro watershed level, even Modis should give us a good signature. Um, so in fact, for some of the other data points like drought incidence, so whether an area is to be declared as a drought area or not, over there the thresholds defined by the government on some indexes like VCI and moisture adequacy index. For those, we are actually using MODIS only. Because there we don't necessarily need to go down to the farm level, but MWS granularity should also be okay.
We can also integrate Sentinel-1 time series data that is available as 12 days interval and highly, we can say, reflectable for crops like soybean, cotton, maize crop, and also for the minor crops as well, but not on the minor side, on the higher side, with the crops which has higher canopy or bigger canopy. So those data sets are highly useful.
Yeah, absolutely. Yeah, Sandeep. Yeah. So those Sentinel-1 can be very helpful when it comes to crop classification, because like you're saying, it captures a lot more information about the overall structure. Whereas Sentinel-2, which is optical data, that captures more information about, in general, the greenness and phenology. Yeah. And in fact, there is a lot of work going around this whole space of remote sensing foundational models. So over there, uh, putting data together from Sentinel-1 and Sentinel-2 also is very helpful to get over the any missing data points for cloud cover. Yeah.
Okay, sir. Got it.
So not
Thanks.
sure if everyone is aware of these things. Basically, there are two types of satellite data that typically come in. One is optical data, which is basically observing the reflection from the whatever sun's energy is falling on the earth and it is getting reflected. So satellites are photographing that, right? So they're basically just seeing what is being reflected. And this optical data therefore gets affected by cloud cover. That between the satellite and the Earth's surface, if there are some clouds, then obviously the satellite can't see what's below that. Yeah. So that is Sentinel-2. Yeah. Sentinel-2 gives optical data as well as Landsat 9, Landsat 8, Landsat 7. They are all optical data satellites. Yeah. There is another kind of a sensing mechanism, synthetic aperture radar. So Sentinel-1 is a SAR satellite. So these satellites actually send radar pulses to the Earth, and then they look at what is being reflected. Yeah. And now the frequencies that are used for this, they can bypass clouds. So the advantage with Sentinel-1, therefore, is that you get images throughout the year. Yeah. It's not getting affected by cloud cover. Yeah. Whereas Sentinel-2 images get affected by cloud cover, right? But of course, both the things measure different things, right? So Sentinel-1, which is getting this backscatter, that is good for tracking the texture of the vegetation. Um, then the SAR data also is at different bands. So some bands get reflected from like the top of the vegetation canopy. Some bands are able to go deeper and they get reflected from the hardwood, right? So they are good at sensing the tree structure. Some go even further and they get reflected from the surface. So they are good at sensing the surface texture. That is it if it is moist, then that also gets captured in some of these kind of aspects, because moist soil is smoother, other soil would not be as smooth, right? So many research works have actually tried to also fill in wherever there is missing Sentinel-2 data. They try to fill it by learning from Sentinel-1. Yeah. And if you build some recent work in foundational models, they actually use both satellites together to do all that. So in fact, Google has put out these embeddings. So it's they use Sentinel-1 and 2 together. Then another a very interesting foundational model called Tessera from the University of Cambridge with some collaborators, right? They also do Sentinel-1 and Sentinel-2 together. And that's very helpful in uh, getting over this problem of cloud cover during the monsoon season. Yeah.
So,
Yeah, Trisha,
have
you have
we?
Yes,
some
sir.
questions? Yeah. Yeah, go ahead, guys. Yeah.
Hi, Professor Adi. So, before, just to take a step back, trying to understand how this cropping intensity was done using the various indices. But before that, I remember seeing a previous post by CoStack where you said that, say, global models such as dynamic world might not be best suited to identify land classes over regions like India. So, I'm trying to get a sense of whether cadastral maps were used to delineate the farms before this cropping intensity was measured, or if there's any other global model that was used for this.
Okay. So actually, maybe let me share my screen. Kapil, if you can
Yeah, I'll
unshare,
stop.
then I'll also share. Yeah. So there's a couple of points. You're able to see my screen?
Yes.
Yes.
Okay. Yeah. Um, so first of all, actually, let me check. Did all of you get the overall setup? So I made this post today about how the data is actually getting populated. Yeah. Right. So basically, first step that we do, we use the digital elevation models, right? The DEM captures basically the elevation of each point on the Earth, right? So DEM basically, right, it is like a 3D map of the Earth's surface. Yeah. But from the DEM, what is done is that there you can start identifying different catchments at different of different sizes. So, for example, you start with river basins, right? Which means that any water kind of falling in this area is flowing into the Ganga, right? So this is the upper Ganga basin, right? This is the lower Ganga basin. Then you have sub basins. You can start dividing sub-basins into watersheds and further into what we have been calling micro-watersheds, right? So now this one is, of course, right, almost 250,000, 300,000 kilometers square, right? These ones are smaller. These ones are watersheds are now about 10,000 or so km square. Yeah. Then these ones are about 1,000 hectares, right? So about 10 km square. And this is pretty much also the size of a village. So if you were to overlay a village map over the micro watershed map, you'll see, I mean, there will be intersections, but you'll see the size wise, right? One micro watershed could probably be intersecting with one or two or three, four villages, right? Around it. Yeah. So once you have these boundaries, the boundaries themselves are derived from this digital elevation map only, where this DEM map we segmented based on, right? So for each pixel, this is a 30 meter by 30 meter pixel. For that, we have one elevation value. This we determine, right, that for each pixel, what is the next pixel into which the water will flow, and various steps after this, right? You get what is called a micro-watershed boundary. So this thing essentially, so for our purposes, it's just a boundary. It's just a polygon. Yeah, the characteristic is that it has one outlet and it can have one or two or more inlets. So the advantage is that you can now, so these are called hydrology units. That basically whatever rainfall is falling, that sort of stays over here. Um, and you can then calculate that of this rainfall based on the soil type, how much will run off. So if it runs off, it gets into these drainage lines and from there it exits the micro watershed. Yeah. And the remaining sort of goes into the ground from where it might get pulled up by crops and vegetation. So that is evapotranspiration. Evapotranspiration then measures how much of this water which sort of went into the ground has now evapotranspirated. Yeah. And if this rainfall minus ET minus runoff is negative, it means the deficit is either groundwater being pumped up, yeah, or there are some canals or something which are bringing extra water into this setup, yeah. So this was, I took a slight detour, right? But just to make sure that, right? So ultimately we get these micro watershed boundaries, yeah. Then for data on cropping intensity that we were seeing, right? Now that data is basically calculating that in this micro watershed, yeah, how much area was under single cropping, how much area was under double cropping, triple cropping, and so on, right? So how do we get that? Yeah, because now we have a polygon of about 1,000 hectares. How do we get that, right? So for that, we first have to, for each pixel, we need to map each pixel that is it growing one crop or two crops or three crops, right? So these are what are called rasters, yeah. And this is the LULC land use land cover raster. Dynamic World is a product that's available on Google Earth Engine by Google itself, which also produces these LULC rasters. Yeah. So what can be done is that if, for example, you want to find out how much area in this micro watershed is cropping area, let's say, yeah. So Dynamic World will have a couple of classes in it. One class will say, right, that this class means some color means it is a cropping area. Some other color would mean that it's a tree pixel and so on, right? So this vectorization step, what it does is that it takes this raster and it sees which micro watershed for this polygon of the micro watershed, it counts how much area is under this cropping area or how much area is under tree cover, right? So that's how you get some of these stats, percentage area under cropping and so on, right? Similarly, there is a raster that we produce for terrain where we classify each pixel into one of 11 classes. That is it up on a plain area or a gentle slope or like a top of a mountain or top of a flat top mountain and so on, right? So there is this terrain raster. So essentially what's happening is that there are a bunch of these models, different ML models on satellite data or other algorithms. They are producing these rasters. Those rasters we then vectorize. And that is what gives us that particular graph that we just saw. Yeah, that it's now counting percentage area under cropping and so on, right? Now coming to the question, right? What does Dynamic World provide us with? So Dynamic World is so think from Google's perspective that they wanted to build a global product. So the kind of classes in Dynamic World that they have are basically cropping is just one class. Yeah. So Dynamic World is not caring about whether on that pixel only one crop was grown or two crops or three crops, right? They are just saying that that pixel is a cropping pixel, that some farming happens over there. Yeah. And some other pixel is a tree pixel and so on. So the Dynamic World classes are basically classes that have a wide global requirement, right? But now in India, we, right, for our purpose, we also want that we want to understand which areas are single cropped or double cropped and so on, right? So for that, what we basically do is that um, So let's say we use some dynamic word. Actually, we have our own crop classifier to identify crop pixels, but let's say hypothetically, dynamic word is telling us which pixels are crop pixels. Yeah. Then what we can do is that now, like we were saying, we are building these fortnightly time series, right? Because Sentinel and Landsat, all of these have revisit days. Yeah. So we can actually build a fortnightly time series for each pixel. Yeah. So for each 10-meter by 10-meter pixel, we can use all the data that Sentinel and Landsat have captured to construct a time series, right? Now, these time series can also be, there are multiple spectral bands that are being captured. Yeah. So the satellites are capturing the red band, green, blue, infrared, near infrared. Landsat also captures land surface temperature, right? So a lot of these different bands. So you can think that there are like 14 bands, so 14 time series. Each pixel you are representing in terms of like 14 time series. Yeah. Uh, NDVI, right now, which of those time series reflects cropping signatures, right? So one very common cropping data point, index that is used is NDVI, normalized difference vegetation index. Yeah. So NDVI is just calculated based on, you can just check the formula, right? It's basically some band X minus Y upon X plus Y. It's a normalization of some of these things, right? So, right now NDVI reflects greenness. So if you plot the NDVI time series, so this is over 2 years, right? This is 1 year, this is another year. So now you would basically see that we get one peak, right? Or you might get two peaks, or you might get three peaks. Yeah. So now for each pixel, therefore, if you're able to count the number of peaks, then you can say that that particular thing is a single crop or a double crop or a triple crop, right? Or based on the timing of the peak, you can say that this one was cropped during early monsoon. This one was cropped maybe after the monsoons, right? Actually, this is an interesting class. You normally get this class in areas just around rivers and water bodies. So what happens is that during the monsoon, the rivers are flooded, but after the water recedes, then on the river banks or areas which are waterlogged earlier, over there sometimes cropping is done. Yeah, so that's why it's called single non-kharif. Yeah. Double cropping is basically, right, you planted something in Kharif and then you planted something else in Rabi, right? So this is like a typical paddy wheat kind of a system that during monsoon you plant paddy, during Rabi you plant wheat, right? Or you can do, right, maize and pulses in the second season. Right, triple cropping is where, right, double and triple normally happen if you have access to irrigation. Yeah. Here it is mostly rain fed. The rains will come and they help water. If the rains are delayed or there is dry spells, then you might need some what is called protective irrigation. That perhaps you want to use some groundwater pumping, or if there is a pond, then you might want to pump water from the pond. Yeah. So structures like farm ponds help, check dams, they help a lot for protective irrigation during Kharif, uh, and which is getting increasingly important because there's a lot of erratic rainfall now. Yeah. Double and triple cropping would normally require irrigation where the water will either come from canals or groundwater pumping. Yeah. So triple cropping is where you might grow some vegetables or something also during the summers. Yeah. So what, right, long answer to your question, right? Basically, that's the idea that to get these classes, the method that we followed is we basically, for each pixel, we build the time series and then in some sense we do peak counting. Yeah. But it's a bit of a roundabout way of doing peak counting. We basically, what we do is we pick up cropping pixels from all across India. Yeah. And we build time series of all of these cropping pixels. And then we cluster those time series um, into some uh, high level clusters that begin to indicate that in those clusters, some clusters very visibly have one peak. Some clusters very visibly have two peaks. So we say those are double cropping clusters and so on, right? So that's how this is done. Yeah. Yeah.
Thank you so much,
So
Professor.
yeah. Yeah. So I'll just right. So and ultimately now imagine that you're clipping this, right? You have some micro watershed over here. Yeah. So then on this micro watershed, you can count how much percentage is single cropped, how much percentage is double cropped. Yeah. And that's how you get those time series. Yeah.
Thank you for that. Um, uh, I I had one more question. Um, have the embedding models from Google, like Alpha Earth, or those been useful so far in this project, or have you tested them
Hmm.
in any manner?
Yeah.
Or
Yeah.
can we also build like small models based on them, so that we can predict specific things and run on like common devices instead of always having to rely on Google Earth Engine?
Hmm. Right. So couple of things. So we haven't used these embeddings in the data that's out there right now, but we are building a version 4 actually of the LULC, which uses these embeddings. So that's much better now from the current version. Um, right. But the second part of your question, right, that can we build local models? Do we need to use Earth Engine and so on? So one of the issues with using geospatial data is that um, if you have to build, you have to bring the compute and the data together, right? So like we were just saying that for some of these cropping intensity things, right? For each pixel, we have a time series, right? So now you can imagine, right, that even, right, 10 meter by 10 meter, you can start thinking, right, that for each of these pixels, you would have 14 bands and over a time series, about fortnightly would give you about 25, 26 data points in a year. That amount of data needs to first be downloaded, right? And then you can do some machine learning and things on it. So, uh, so whereas Google Earth Engine, one of the main advantages is that it is hosting the data, right? So it's already regularly pulling in data in near real time from Sentinel and so on. Um, uh, and it is also providing you a computation environment, right? So you can write your scripts, or what we do for most of our stuff is we use Python APIs to fire off compute on Earth Engine. So the bulk compute which is happening is all happening on Earth Engine, and the data is also co-located over there. So that it's easy for the computation to happen, right? And then we download the output. Yeah. So that's the kind of strategy we've been following. Yeah. But of course, right, we all do need to realize that there is a limitation, right? Because we are relying on Google, we are relying on them providing all of this computation infrastructure also basically for free. Yeah. Uh, uh, and right, but it does take away a lot of infrastructure hassle, right? Because otherwise, the alternate scenario is that we download everything locally and we use GPU servers and other things to process it, or we do it on AWS, right? A term that's popular in that sense is cloud native geospatial computing, right? So what cloud native is basically doing is that you're assuming that a lot of these data sets are on AWS, let's say, on their S3 bucket. And then you get another EC2 instance and you attach GPUs to it, and then you're able to access the AWS S3 bucket and you're able to do your computations over there, right? right? But overall, the point is that you need your data and the compute together to be able to do these kind of things, right? So whichever way it works out, that's the idea. Yeah.
Yeah, thank you. Mhm.
Great. So Kapil, you want to go to the second notebook and yeah.
Yeah, sure it is. I just done it in second notebook. We are again getting the admin detail by let long, state district block, and we have a endpoint which provide you all the layers available as a GeoJSON. And as we previously shared it with you that it's hosted on GeoServer, so it give you the GeoServer URL. You can download that GeoJSON and build data frame and do any kind of analysis. So here we are plotting the water balance by using this API. So primarily we are supplying latitude and longitude, the same step. And here we define an output file in the space, uh, local space of this collab. So we will save this file in that and setting up the header and again setting up the endpoint, and by first API I am hitting to get the admin details. So and this in this step also I am building the query parameters for the next API similarly. So based on the lat long we resolve this Odisha, Angul and Angul, and the MWS ID we are also getting with it. Now the next API endpoint we are hitting get generated layers URL, which will provide you the all generated URL layers for that location. By layers, I mean the data sets, and it's kind of more raw data set. So in this, we are heading that API, and from that API, we separate out hydrogeological layers URL. So it provide you all sort of URLs, right? LULC, aquifer, vector as well as raster, and then this is the URL where I can found it. So if I click on that, this is the raw GeoJSON, which is hosted on the Geo server, and it contains, see, this times series data 1718 for delta G, ET, precipitation, runoff 1819. So this is basically the hydrological data set. If you download the another layer, it will provide you some drought data set. And so now I am opening this file and building the data frame to plot it. So in this step, I am just hitting up and saving those file into the local space. And this function, I am opening the GeoJSON and loading the feature collection. And from feature collection, I'm extracting out of the property. And then in this step, I am just fetching out the data per year. So doing just adjustment in data frame to get the year wise data. And finally, by using this data set, I am building this time series data. So date, year key, delta G, ET, precipitation, runoff, G, well depth, and finally, I am supplying this data. So calling this function time series data and getting this data, and just using this plot matplot function, I am finally building these are all setting up the label and some beautification of the code labels and legends, and then building this water balance. So this first is showing the precipitation and then evaporation ET, but transformation, and then finally delta G. Right. So these are the water balance we are plotting by using the raw data set. Even there are more use cases. We can even fetch the draw data from it and plot it, and even we can fetch the draw data set and figure out the MWS more sensitive to the drought, less sensitive to the drought. And by using our admin boundary, we can fetch the intersecting villages to that MWS, so we can actually index the village based on their drought sensitivity. So there are various example which is possible by using these TI and data set APIs. So yeah, so any question on that?
Right. So just like the previous one, right, where the cropping intensity was the micro watershed values had been pre-computed by intersecting the micro watershed boundary with the underlying LULC raster, right? So in a similar way, actually, what happened behind the scenes for pre-computation, right? That we used rainfall data. The only difference between rainfall and LULC is that LULC is available at a 10-meter resolution. Rainfall is, I think, this one that we're using is at a 3 or 4 kilometer resolution. Yeah. So, so again, we are intersecting the micro watershed boundaries with the rainfall. So we get what is the average rainfall happening in that micro watershed. And just like rainfall, there is a different data set we use for evapotranspiration, which is tracking how much of the water is consumed by vegetation, crops and trees, right? So this ET data itself, in turn, has been produced by researchers by modeling things like the temperature, the wind speed, solar radiation, all sorts of things, right? To finally give that ET data. Um, right? So, and runoff is something that we compute ourselves, but not going into those details, right? But I can imagine that for that micro watershed, for sometimes for 10-meter pixels or sometimes for 3 kilometer pixels, right? There are all these data sets, and those we are intersecting with the micro watershed. So we get that in that micro watershed, what's the fortnightly rainfall, ET, and so on. And that is what the APIs are helping pull out, right? Now, the APIs are helping pull out in two ways. The previous notebook that Kapil showed, the APIs are directly providing the data in a JSON format. This particular notebook is the API is returning a layer, a GeoJSON layer. That layer is downloaded, yeah, and then we parse the data from the layer, right, to extract this, yeah. So this is just to show that there is some data which is there directly in the APIs, but there is the layers actually have some more data points as well. So to get to those, the alternative is that just download the whole layer and extract the data from that, right? Uh, so that was kind of the purpose of these two different examples. Yeah. So conceptually, have you guys tried out? I mean, are you able to invoke the APIs by now and access the data?
I have accessed the data through like simply in your Google Drive, but since the API access is not like publicly available or so, or I can't actually see the button to get API or these things, so I haven't been able to use this particular server or your particular notebooks. Um,
Uh,
I have been using these layers for a long time, but yeah.
Oh, okay. So can you, I mean, just drop us an email, right? We'll try to fix that. So actually, I mean, getting the API key, you just have to register on dashboard.corestack and then,
Yes, I have registered. Um,
okay.
After
So,
that, I don't see any option. I had shared the screenshot in last call also, but still, I don't think it has been saved. I just checked it right now also.
okay. So maybe, can you just write to Kapil,
Yes.
and
Amit, we can
we'll
connect and resolve it. I'll connect you
Yes.
after this call and we can see. Because as I received your email, I have provided you access of that. But we can
Um,
connect and see if there any other issues are there.
okay, so do we need to do something else to get that access, or
No, whenever you register, we receive an email and then we approve. We
I
then
logged in again and it is still the same. I will mail you. Let's
so we
let
will
other person.
connect after this call,
Yeah,
immediately after this call, if you have time and we can resolve it.
yeah.
yeah, maybe you can drop your email also, and Kapil or one of us can write to you. Yeah.
I mean,
Um,
we are also thinking about making this more simple instead of this authorize approving method, but yeah, will be there.
Yeah, we can set up probably some API usage limits and those things so they don't get
Huh, huh.
abused, but still others can use it.
Right, right. So we are also thinking about the same, setting up some throttle limit and setting up some captcha, then we will open it. Yeah.
Yeah, thank
So then it will be simple, just register and create the APIs.
you.
right. Yeah. So yeah, it will be good if yeah, I mean, let us know with any trouble with accessing the APIs, or if you have trouble with understanding the data, just drop an email or drop a message. We'll get back on that. Yeah, and uh, uh, so we'd also put up a bunch of ideas for the challenge. Yeah. Um, do you guys want to discuss any of those, or do you think you understand? Otherwise, I can quickly also just explain some initial thoughts we had.
Hello.
Yeah. Yeah, see.
Hello, Professor Seth. Hello, everyone. I had a question, as you mentioned, regarding the water balance. So I was thinking that why aren't we using any data set for the root moisture,
Sorry for say that again.
for the surface moisture, or now we have the data set
Uh-huh.
like SNAP for the surface
Huh.
moisture for the water.
Right, right. Yeah. No, you're right. You're right. We haven't put in soil moisture as yet, but those are much needed, right? So, I mean, this is again, right, some place where all of you can also help. We can work together, right? Just like we pull in data of rainfall and so on, we can also, in the same way, build those pipelines to pull in soil moisture data as well.
Yeah,
Yeah.
because I've seen that though I don't think in India it is practiced, but most of the places abroad they also practice the tile drainage sort of irrigation. Sort of agriculture practice where the water tables remain high,
Hmm.
tile drainage.
Correct.
In India, it's not. So maybe using the soil water might help.
Hmm. Yeah. No, absolutely. And it can, I mean, there's a lot of interesting predictive stuff that can be done. So soil moisture can be a leading indicator of crop water stress.
Yes.
Yeah. So let's say, I mean, in NDVI or something, you might see the signature much later that
Yes.
the crop is
Yeah.
already stressed by that time. But right, soil moisture and so on can help just give an advance kind of warning. Um, yeah. So there's a lot that can be done with soil moisture. Actually, one larger, broader kind of thing again is on resolution, that most of the data sets are at a lower resolution, km kilometer or something. Um, but even then, it's still going to be useful for some of this analytics.
And one more question I had regarding the cropping intensity. It is that in some regions, the people or the farmers might be practicing single crop.
Hmm.
So that are we able to detect or?
So that we should, right? So what single cropping, the class for single kharif basically means that only one crop is being grown. Yeah.
But during the entire season, throughout the year, for example, crops like sugarcane or uh,
Huh.
now pineapples are also grown in India. They take a much
Yes,
longer
yes.
time.
Yes. So actually the class name is a bit misleading. We are calling it triple crop, right? But actually it could be any of those. It could be triple crop, meaning three crops are grown, or it could be like a long duration crop like sugarcane,
Yes.
annual or long duration crop which is grown. Yeah. So actually, yeah, we need to fix some of that also, because we've also really been learning as we've been building. What we are calling triple actually means basically cultivation throughout the year. Yeah.
Thanks.
Yeah.
Professor,
Are there any sorry?
sorry,
Yeah, please continue.
thank you. Professor, one question we touched upon drought indicators as well. Are there any particular drought indicators? Are those mostly deterministic models, or are there any prediction models for droughts as well?
So, what we have implemented right now is basically the method that the government of India uses to declare a drought. So it is all ex post, yeah, that after the drought has happened, you want to determine whether, I mean, after some time, you want to determine whether a drought had occurred or not. Yeah. So internally, it uses criteria like whether it's what's called a meteorological drought, meaning that the rainfall in this week was much lower than the rainfall typically expected in this week based on the last 30-year average, let's say. Yeah. So something called rainfall deviation. And that way, there's a bunch of other parameters that they use. And also, did this result in a agricultural drought, right? So for agricultural drought, they then say that, well, is the vegetation condition much lower than the average vegetation condition expected at that point? Yeah. So, so the drought indicators that we are giving over here are the implementation as per the government of India. Yeah. We will soon also add a more standard index called SPEI, Standardized Precipitation and Evapotranspiration Index. I forget the full form. But SPEI is a more globally accepted standard index, right? That a particular range in between means very severe drought, particular range means less severe, and so on. Conceptually, is kind of similar, that you compare the what's happened in that year with the average over the based on the history of that thing. Yeah. But these are all ex post. Yeah. I think what you're asking, Shreya, is that can we forecast whether a drought is going to happen or not? Yeah. So that then needs other kinds of things, right? Again, we've not ingested, but these are all great ideas that can be built up, right? That uh, Google, for example, now provides forecasting data about 14 days into the future. There might also be data at more, right, at a time scale of months of climate forecasting. Yeah. So those things can potentially be used as an early warning that we are expecting drought conditions in the next couple of weeks, or let's say next or in this season, right? And that can be very useful for crop planning, for example. Yeah.
Understood. Okay. Thank you, Professor.
Hi, Professor. This is Sabya Sachikaviraj from Deloitte.
Yeah. Yes.
So I just have a small doubt that like this many works has already been done, right? So these are like wonderful to see that, and it's been a wonderful presentations and everything. So I just want to try to understand what is the difference between the real scenario versus our model scenario, what we are doing, and in terms of accuracy, in terms of crop classifications, how it is the deviations, the percentage of deviation from the real world, that I want to understand.
Yeah, Sabyasachi. So actually, I mean, all of these things which are model generated, for things that actually the technical manual is really the best place to take a look. So for some of the models that we have done ourselves, we have put out accuracy numbers based on whatever ground truth is there. Um, so like for cropping intensity, there's accuracy, at least in the Karnataka region where we mostly did that ground truthing, it's in the 85-86% region. For some other classes like crop and trees, where we have a more pan-India ground truth, it's very high, 95-96%, right? But there is need for constant additional ground truth for understanding all of these aspects and how well are these models doing. Yeah. Um, uh, and likewise, for any external data that we're using, like rainfall, for example, where we are using data from JAXA. So they over there, similarly, many of these have been compared with ground stations that IMD runs of rainfall and so on. So we have tried to use data which is uh, more or less accurate in India. But of course, right, we have to take this with a pinch of salt ultimately because there will be inaccuracies. And uh, so we do need to keep our eyes open, right, to understanding where are they working well, where are they not working well. And ideally, in the long run, we want that the core stack should also become more plug and play, that you can say that, okay, this data works better in this region and some other data set works better on coastal regions and so on. So ideally, it should become something like that in the future. And yeah, all of these are places where all of you can support and help build it out.
And another thing is, do you think that spatial resolution of this Sentinel-2 or whatever open source data we have right now, and that is sufficient to map like farm level, or you can farm level crop classifications, or like how this spatial resolution impacting our accuracies in crop classification?
Yeah, so actually, for crop classification specifically, I don't think the spatial resolution is the challenge. Rather, the ground truth, getting good ground truth is the challenge. Um, so, some of these foundational models like Google's Alpha Earth embeddings and Tessera's embeddings, they are very good at capturing the time series characteristics. So the way you distinguish different crops from each other is largely based on the time series of the crops. As some crops will have a fast green up, will have a slower green up, and the extent of green up, right? Those are the typical characteristics that ultimately help us identify what's the crop. So so from Sentinel, we get 10-meter data, and which is what ultimately results in these embeddings. The problem is that in India, there's not enough ground truth data available. So many agri-tech companies are able to do a good job, right? Because they have enrolled farmers, and the farmers have walked around their plot. So now the satellite company knows, sorry, the agri-tech company knows that this plot belongs to which farmer. And the farmers have also reported what crop they're growing. So gradually, this data set becomes quite large, and then you can use it for machine learning. Yeah. And yeah, but the problem is that with agri-tech companies, all the data sets are closed, right? None of them are open. So from an open source perspective, what we really need is if some of these data sets can be opened, or, we build our own kind of an open data set. I think that is the main bottleneck. Yeah.
Yeah, so some of my friends, they're working on Haryana Space Application Center, and still they are doing this crop classification manually from using the satellite image of Google Earth. So they are using that, and manually they're digitizing, and they are thinking that doing automatic or automated way may not be a proper solution to take a decision in at the government level or make any policy for that. So that's what they are not that much interested on doing these things. They are interested, but the result is not as per their expectations. So whatever resources they are hiring, they are directly jumping into the manual digitization. So, and the variety of crops are huge, like banana, like small crops are there. So, and they are very much dynamic, like within 10 meter, you will get dynamicity. So when we are telling that 10-meter resolution is enough, or you're saying that, so in India, such some regions like in West Bengal, some these areas, and then Madhya Pradesh, these areas are the farm size is very small as compared to like Punjab, Haryana, and all. So doing crop classification in Punjab, Haryana compared to this West Bengal, Madhya Pradesh, and Chhattisgarh areas is totally different. And when you run the same model with these two different regions, and the output may sometime differ, like so that's the reason maybe government entities they don't want to do this automatic way. I want your comment on this, how it will be.
Yeah, no, you're right. So, I mean, it's things that things should be tested. But I mean, on the other hand, many people have reported being able to do good classification in areas in Bihar, for example. So there are some papers from Meha Jain, who's right. So they did field data collection in Bihar, and I think Jharkhand as well, and they were able to do quite well. So, so yeah, I mean, the point is that these are, in some sense, these are all research-oriented questions, and unless we don't actually do it, it's hard to really say what's going to work or not. But if we do have much better ground truth, then we can see, yeah, to what extent even Sentinel can be useful. And then even more than Sentinel, as long as it's the government, right? I mean, if they're doing it internally, then they've not opened up data from many ISRO and other things, but actually they do have access to even higher resolution data, right? So some of that can also come in handy. Yeah, but you're right that the farm size, of course, makes a big difference, right? So larger landholdings in Punjab, right, versus much smaller parcels in other states, right? So there are big differences for sure. Yeah.
Sir, can I also explain about this, as I have good experience around this crop classification in agri-tech sector?
Yeah. Go ahead, Sandeep.
Yeah. So like I'm working in this agri-tech industry from last 8 to 10 years. So what I found, yes, on somewhere like he explained, it is fine. And in working in Punjab, Haryana, UP is slightly easier as compared to you can say Chhattisgarh, Jharkhand, because of the farm size. And in Punjab, Haryana, farm size are quite good, and we can easily derive the crops using Sentinel time series datasets, whether it's a Sentinel-1 or Sentinel-2. Okay. The cropping phenology, sowing time, harvesting time, peak season are necessary to understand. But wherever we are facing the smaller farms, where the overlapping is happening more in terms of like if the adjacent crops are different from each other, they are the problems found. Okay, the ages of the farms are not up to the mark. Also in the crop mixing, like I can give you an example of Latur district, where tur crop was mixed with soybean. So there is a large extent happening. So that is very challenging to derive the specific crop on this part, specifically in the Kharif season. And these SAR data sets are helpful to derive the soybean, cotton, maize, paddy, sugarcane as well. So some major crops can be derived using Sentinel-1 data, but like on the vegetable side, like onion or tomatoes or green chilies are slightly challenging to derive from Sentinel-1. But the mix of both of the data sets are quite useful for the crop classification. And from the automation point of view, okay, like Kabiraj says, in India, the farm size is very small. We tested out the automation in some part of Bihar, some part of UP. And we had a machine learning team who tried their level best to derive the automated crop classification. Somehow they succeeded, but it was very challenging. But the models which we executed in the US region, America or Europe, that was very well executed. But whenever we are brings to the things in the Indian context, are seriously challenging. So from the scientist perspective, like what MNCFC or other organizations said, the accuracy differ from region to region. It may have 85% plus, it may have 70% or 65% as well. But the crop mixing happens usually, specifically with Sentinel-1 and Sentinel-2. But if you talk about the freely available open source data, I think that is the best to use Sentinel-1 and 2 as time series. And if you go for the commercial, that will be very expensive if you use for the classification. Yeah, thank you.
Great. Cool. Are there any other questions for today?
Just one question if possible.
Yeah.
Okay, so it is around some technical lines. It is on some technical lines. So I was basically just wondering, like on Google Maps, we can see the boundaries of walls or those things at around 1 meter scale, or even smaller things are visible from space somehow. And even then, we say like in the Sentinel data that we get is like one like a set of bands per pixel, and that is 10 meter. So how is this different? Why like how the Google Map is more precise in terms of, and the Sentinel ones are not?
Yeah, the Sentinel is free. The Google Maps are not free. I mean, in the sense that it's not free for download and analysis. So in Google Maps, they use data from a satellite called Maxar. It's a paid matlab setup. So Google buys images from Maxar and they make those available on Google Maps. Um, but they have a policy that this data is not for analysis purposes. Yeah.
Yeah,
So
in
you
a
can.
sense, but
Yeah.
we do have, as a human, especially, we do have
Mm.
capabilities. I'm just wanting to.
Yes. The satellites are capable. There is a difference also, though, that I mean, on the Maxar, the what we see on the Google Maps is just RGB data, right? Just the visible bands. Um, whereas Sentinel also has other sensors on it where they can provide infrared and several other bands, right? Um, so different bands help us understand different kinds of characteristics. So that's one plus point with that. Maxar, I don't know if they provide other spectral bands as well. But again, it's paid, right? So so Google buys from them, but it doesn't make it freely available for everyone. And then similarly, there's another system called Planet. Planet provides about 3 to 4 meter resolution. In that, they provide RGB and also near infrared. So that can be used for several vegetation things as well. But Planet, again, it's not free, although in some cases you can ask for like academic or educational purpose access and they do grant it. But that's the other one also. Yeah.
But like on a country scale, we could have projects with ISRO and those kinds of people to enable this in that sense.
Yeah. So ISRO also has satellites which are quite high resolution. But again, that data is not openly available as far as I know. So that's one of the issues over there.
Yeah.
To jump in, I would say that Maxa WorldView, they have other bands also available, near infrared, this red edge, and the short wave infrared bands also. But if you want to spend $20 per square kilometer,
Yeah, 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 that's the thing. Yeah, yeah. But these things are going to get better eventually. I mean, yeah, there's also hyperspectral satellites coming in that, right? So like uh, Sentinel and so on, they provide about 12 to 14 bands. Hyperspectral satellites will provide about 1,000 bands. Yeah, so which means that every small sliver of spectrum, right? For that you're getting a value. Yeah, but yeah, those are still yet to come, and uh, they'll all be paid. So we've got to wait for the government or somebody to set up these satellites and provide open data. Sentinel is a European system, Landsat is an American system, right? So in some sense, a lot of this is happening because of public funded massive projects. Yeah.
Yeah. Thank you.
Yeah. Okay. Great. So, folks, please ask questions. Yeah. And any issues, right, we'll very quickly resolve. Yeah, feel free to ask anything you want about any of the technical stuff or about any of the ideas we've also put up. And um, yeah, so please don't feel shy about any of this. Um, we've also started to have interest. So one of our partners, INREM, they work on water safety. So they collect a lot of measurements on water pollution, arsenic contamination, fluoride contamination, right, other pollutants, and they have proposed a project. I'll send that across also. If any of you are interested in that, then Sundar from INREM and their team would be very happy to guide. Um, and right, so what they want to do is that they have all these point measurements, yeah, across India of water safety at different points. So they want to take these point measurements and see can we first can these points are close to which rivers, for example, right? Because then you can kind of uh, um project in some way that like an arsenic contamination measurement that was done because it's next to a drainage, it's likely that uh, things downstream, this water might be flowing over there. So Sundar has given a lot of interesting ideas on how some of these water safety measurements can not only be used to produce wider maps, but they can also inform other kinds of structures. So aquifer mapping, unfortunately, is right. It's not easy to map underground aquifers, but again, if you know the chemical signature of water at one point and chemical signature of water at another point, then you can determine whether they're part of the same underlying aquifer or are they different aquifers. So a lot of interesting ideas that Sundar has given. I'll send that across. And yeah, so please, you guys, right, ask questions. And we've given a bunch of ideas in the CoStack challenge. Another bunch of ideas. I'll send the links again. Of open ideas around new data sets that we can bring in. Like here also one of you said that soil moisture will be something good to bring in, right? So these things will be very nice. Please keep it interactive. And yeah, because the whole thing is too large for anyone to build alone. And right, we really want to make this into a large open source effort. Yeah. So it will be great to get participation from all of you. Yeah. All right. Okay, folks. Yeah. Have a good weekend, and
Thank you.
we'll touch base next week now and send emails in between. Yeah.
Okay. Yeah. Thank you all for
Thank you,
joining
sir.
this call.
Thank you.
Yeah.
Thank you, everyone.